Until we get further on in our education in APChem, we're going to just define an acid as any compound that upon reacting produces a proton, which is an H+. And a base is going to be any compound that when acting in an aqueous solution accepts a proton, or for us right this moment in time has an OH- associated with it. So a neutralization reaction is a specialized type of double replacement reaction where an acid and a base are mixed. The products are always a salt and water. Please recall the definition of a salt. And a salt is not just the stuff you put on your French fries, but a salt is a ionic compound that has a metal and a nonmetal, or a metal and a polyatomic ion. So hydrochloric acid and NaOH does make the French fry deliciousness plus water. The net ionic equation, when we take out those things that are the same on both sides of the equation, looks like this. A really short way to look at an acid and base titration for right now is to know at the equivalence point, at the neutralization point, the moles of the acid are equal to the moles of the base. We'll go into this in much more detail later. But all you have to know right now, at neutralization, the moles of the acid equals the moles of the base. You do need to take into account the number of protons, hydrogen ions, that an acid can furnish. For example, sulfuric acid has 2, calcium hydroxide has 2 OH. So we're ready to do our problem. What volume of a 0.1 HCl solution is needed to neutralize 25 mLs of NaOH? That would be HCl plus NaOH combining to neutralization with a salt and water. Okay? Using this equation, the molarity of the acid is 0.1 times its volume, which we don't know, times the number of hydrogen ions is 1, can be neutralized by NaOH that has a molarity of 0.3, a volume of 25 milliliters, and has 1 OH group associated with it. 0.1x is equal to 8.75. X is equal to 87.5 mLs of hydrochloric acid are needed to neutralize our base. In a slightly more interesting problem, in a certain experiment, 28 mLs of HNO3 and 53 mLs of KOH are mixed. Calculate the amount of water formed in the resulting reaction. What is the concentration of H+ or OH- in excess after reaction goes to completion? This gave you a clue that you need to do a limiting reactant problem. So our reaction looks like this. HNO3 combines with KOH to form KNO3 and water. I'm going to write water, HOH, for a reason that will become apparent in a moment. This is a balanced equation. Alright, when we're doing a stoichiometry limiting reactant problem, we cannot use molarity, we can use moles. So I need to know the number of moles of NaOH that are equal to, let's recall, if molarity is equal to moles divided by liters, moles should be equal to molarity times liters. So the moles of an HNO3 are 0.250 molarity times 0.028 liters. The number of moles of KOH, given its molarity, 0.320, times its volume, 0.053 liters, is moles of KOH. To find the limiting reactant, I will find the number of moles of water that each makes, and that will tell me the one that runs out first. The one that makes the fewest number of moles is the limiting reactant. So starting out with 0.0700 moles of HNO3, using its stoichiometry of 1 mole of HNO3 will yield 1 mole of water. I see I can make 0.00700 moles of water. The number of moles of water that can be formed by 0.0170 moles of KOH, probably can do in your head. So our limiting reactant is the HNO3. So the amount of water that can be formed, if you say we had to do in grams, so I'm lazy, so I'm not. A mole is an amount. So the number of moles of water that can be formed are 0.00700 moles of water. That makes HNO3 the limiting reactant and KOH the excess reactant. The second part of this says how much excess reactant is left over in the beaker after this goes to completion. Well, we know that when 0.07700 moles of water was formed, some of the OH from the KOH was used up. We need to figure out how much of the KOH is tied up, the OH is tied up in the water. We know that for every 1 mole of KOH, we have 1 mole of OH minus. So if we have 0.0170 mole of KOH, we have 0.017 moles of OH. So I would like to know the number of moles of OH that are bound into hydrogen ions when this much water is made before the reaction stopped. 1 mole of water contains 1 mole of the hydroxide ion. So we started out with 0.017 mole of the hydroxide ion, and we used up 0.007 moles in the reaction. So we have left over in the beaker this many moles of the hydroxide ion. The beaker has liquid in it, and we want to find molarity. Molarity is the moles of the OH times the volume of the solution in liters. That would be 0.028 milliliters of the acid plus 0.053 liters of the base for a total volume. And the molarity of the excess reactant is 0.123. Okay,